So what I'd like to do is talk about the way in which we can think about risk, and in particular systemic risk, and the impacts that different types of regulations can have. Now, I think we can all agree, this is 10 years. What we may not realize is that we're already at 10 years after the financial crisis. And still, there's a lot of impact of what actually caused the financial crisis. And if we just looked at the recent turmoil in the markets with the VIX, right? That was, some people are saying it was a flash crash. Some people were saying it was manipulation. Some people were saying it was just real volatility within the market and people responding in different types of ways. But none of that was built in to the risk metrics. And it was in some ways a very much of a surprise. And the question is, under what conditions does a case like that, where that's risk is always present in everything we do, what case would a risk within the market leads not only to volatility that we should all anticipate, but fundamental systemic risk? And how can we think about that, measure about that, and mitigate that through a variety of different instruments that we have, one analyzing it through different types of enterprise risk management tools, as well as the way in which we think about it through government regulations, different types of interventions by regulators, whatever those may be. Okay, so we can all understand that the financial crisis really was a point for us all to think about how risk interplayed with the way in which regulations can mitigate risk and what their impacts are. And the crisis was not only a stress test on the soundness of the existing regulations, but it also provided a way for us to evaluate what regulations are best suited to mitigate various types of financial risk. And this discussion is actually even more important now as we think about Congress beginning to roll back some of the regulations that were introduced in the Dodd-Frank Act all the way back in 2010. So I think this is important. And what we see is we don't want to just arbitrarily roll back all those regulations and put us in perhaps even a worse position than we were back in 2008. So this is in some ways the context in which a lot of this work is taking place. And what we show is that data science really provides a new solution to measuring and predicting systemic risk within the financial system. And moreover, it provides a way to test a priori the impact that regulations have before we actually act them. That is, before we actually blow up a financial system. So that's a good thing about data science. That's data for good. All right. So let's think about, there are really kind of two ways in which we want to look at this. First, we want to look at some of the existing solutions, which is going to be regulation. Then I'm going to look at some of the new attempts that have been thought about understanding the impact of regulations and understanding systemic risk, first and the AI analytics. So here. So the current solution really relies on what we would call expert judgment, right? That is, you have people who are very much experts within the field, think about rules and compliance and guidelines, and what they know the impact of those variety of different rules and regulations are on market performance. Okay, they then evaluate the effectiveness of those rules and regulations after the implementation of these rules on the real system. So did VOCA work? Did increasing capital ratio requirements actually mitigate the different types of risk and provide the absorbing capital buffer that was necessary, and so on. Proposed solution, again, focuses on the use of data science. In particular, it relies on AI. It relies on quantitative models to predict the impact of financial regulations and evaluate those before we actually implement this is we're going to use simulation based on real data to construct a financial system, to understand trades at the micro level, aggregate it up, and then do interventions on various financial regulations on the system and ask different questions, test different hypotheses on that system. Okay? So how would you do that? That's a hard thing to do. There's really two steps in this. First, we want to treat this as a classification problem. What you want to be able to automatically classify regulations as systemically risk-inducing, reducing, or not. Right? First of all, we're going to start within a single financial system. So we want to make the first problem small and tractable. And then you want to apply the classification problem to large random sample of financial systems and then run statistical robustness analysis. Now, the first step is already non-trivial, and so we're going to focus most of the conversation today on building out that first step. But some of the scalability discussion will come at the very end of it. And Tim, did you circulate the paper too? I don't know.
No.
But the paper I have a paper that actually starts presenting the scalability and the robustness estimates and moving this into financial systems and so on. And so I'll present some of the preliminary analysis associated with that as well. Okay. So, how are we going to do this? First, then, in order to classify a regulation, all right, what are we going to have to do? We're going to have to find a measure of systemic risk for any given financial system, right? And that's hard because OFR and others find 31 measures of systemic risk, which means there are no measures of systemic risk. And then we want to quantify the impact of that regulation as measured by another metric, all right? So how are we going to do this? So, as I said, there's really no widely accepted measure of systemic risk. And in fact, the Office of Financial Research, which sits in the US Treasury, has identified 31 measures, and I assure you there are more than that. And these include measures of market stress, say in housing and government bonds, COBAR, which is the correlation of various asset losses, Granger causality, which is the correlations between different types of bank assets, macro level in-out data, the flows data, and so on. And this is interesting because this is in sharp contrast to quantifying non-systemic bank level risk, which is really quite well developed, which has very standardized metrics, and are used very much in practice both on understanding their PL statements and have to be reported to regulators on a regular basis. They are mandated by law. So we have metrics out there that are common among all banks that have to be reported in a very consistent way. They're done at the enterprise level. And you would anticipate then there might be a relationship between that micro way of thinking and the more macro systemic level. And we want to leverage that idea. Okay? So what are the analytical steps? We want to look at financial regulation and understand that it's going to affect an enterprise, a firm, and a financial system at 3 different levels. One, it's going to affect a bank and its trades, its micro, most individual level, and its counterparties, who it goes into business with, say JP Morgan entering into a contract with Goldman, and then at the system, how it aggregates across all of its different counterparties, okay? Therefore, we need to predict the impact of these regulations at all of these levels, if in fact we want to understand or simulate the impact of a regulation on a system moving forward. So step 1 is to model a bank's what we call production process, from soup to nuts, from the ground up. You want to simulate the impact of the financial regulation. And here I'm going to focus on one, and that's going to be collateralization. That is, when you enter into a contract, you're going to put money up front, right? This is the simplest way to think of it, up front, so that if somebody fails, you have some money in security that you can take home. Okay? So it's a way to minimize some of that risk. And then we're going to evaluate the impact. Again, we're going to rely on the established metrics on trade and bank level data. And then we're going to use systemic risk metrics as a way to act as an aggregation of each of these metrics. And I'll show you what that means. How are we going to do that? Well, we're going to build off of some graph model theory. And we're going to represent a financial system as a graph, G. And this is fairly well known, but it's actually an interesting way to start thinking about a financial system because it'll have interesting properties that we can then estimate and start measuring. The nodes will represent the counterparties. Arrows represent trade relations, right, back and forth. Weights of the arrows going to represent the risk associated with each of those trades that's induced from one counterparty to the other, right, from the tail to the head. So if we look at A is imposing, say, 300 million euros on B. B is imposing 500 million euros on A. A imposes 500 million on D. And so that would just be the way to read those flows, okay? Ask questions along the way if there's any, if it's not clear. All right. So you can see just right there. Now, in doing that then, the metric of systemic risk should take into account the sum of all the weights of all of those arrows, right? Both the in and the outflows. We're going to maximize the risk induced by any counterparty A. So the absolute value of some omega A is just the weight as the sum of all those weights of the arrows. Right, so when we look at A, we saw that the positive row, A, is going to be the ratio of all of the stuff all of the weights that A pushes out towards everybody else. So 300 to B, 500, 200. A pushes out 1,000, and then the row plus A would just be 1,000 over 2,700, which would be 37. So it's just a very simple proportion relative to the system as a whole. Now, having done that, we can then think about the classification problem, right? The binary decisions, and we're going to think about it in three ways. We're going to think about what we need to do in inputs, how we're going to do the simulation, and then how we're going to think about our outputs and how we're going to use those outputs. Of course.
So are all the regulations representable by this kind of graphs, or are there ones which are not represented by this kind of graphs?
Nobody's ever represented a regulation like this before.
No, I'm not trying to say that. I'm just saying, every regulation can we do it? Yes. Is there a theorem which can be proven that?
Yes. So can I actually take the essence of most regulations and define it, whether it increases or decreases sort of the risk, or how it changes the levels? Yes, I can. Okay, I can find out what capital ratios do. I know what that does, so I could just actually calculate that out, because I'm going to show you I have an engine, an open source risk engine, that's going to allow me to calculate at each of those stages. Okay, so yes, I can calculate. There are ways to calculate each of the impacts at the trades, the counterparty, and then what we add to this is at the system level. Then what you do is you compare with no regulation, what happens with no regulation, that's your base, and then what happens when you have the treatment, the intervention of a regulation, okay? And that gives you your comparisons, all right? So I'm gonna do this with one, which is collateralization, and yes, it can be done with many.
So capital flows and other kind of things will be done.
So capital flows,
so which is a part of the risk market,
is actually part of the outcome, is actually part of the outcome variable. That's not a regulation. That's something that's almost the input output. That's actually what those arrows are doing, right? Those are the sums of each of those arrows are capital flows, because counterparties, you could think of Deutsche Bank and JP Morgan, and if I think of them as US and Germany, when I take the aggregate of all those trade parts, that's US and Germany, that's flows, correct?
So what about derivatives and other kind of
I'm so sorry?
What about the financial derivatives of our
What is the what?
derivatives? Financial derivatives which have been used as a
That's right. So the contract is your financial derivative.
Mhm.
Okay, and that's what the counterparty would be with. Now, the contract itself can be as complex or as simple as you want. In this case, under the new regulations, there are two ways in which you can do a derivative. You can do an over-the-counter derivative, which is a standardized derivative, and you go to an exchange, and it's standardized, and you go through that. Or you can do the things that are off that exchanges, right? Over the counter. One is the standardized exchange, one is the over the counter, which are not standardized contracts. When you do non-standardized contracts, you have to put up additional collateral, if you will, to offset or mitigate the risks that are associated with not using essential party clearing, okay? So this is a way in which understanding how this particular regulation, right, both initial margin and putting up money up front and variation margin, putting up money when there's market shifts, is going to impact the risk that takes place at the system. Okay?
Thank you.
Okay.
Thank you.
And I'm happy to give you a paper that goes through.
I'd love to take a look at it.
Okay, great. I'll do that. But I'm not doing a text-based analysis. I have other work that does text-based analysis of the regulations themselves, right? That's not what this is. Okay, yeah. Okay, so I just want to make sure I'm clear and everyone's with me. Okay, excellent. Okay, so we're going to have a financial regulation R. It could be, like I said, a capital requirement, a leverage requirement, a collateralization requirement, and so on. And then we're going to have a financial system G, which will be defined as we sort with those weights and arrows and nodes. All right. We're then going to use a simulation. We're going to compute a graph model, right, with a simulation G first without the regulation. Okay. It'll have some flows in and out and some ratios along those lines. Then we're going to compute the model with the regulation. And then we're going to obviously do a comparison between them. And then the output then is you're going to evaluate the systemic risk in G in both simulations, okay? And then you're going to ask the question of, has R reduced systemic risk in G, yes or no? So that's the basic way in which we're going to think about this. All right. So now, in doing this then, you have to simulate systemic risk, right? So you want to apply the graph model to the system of banks. You want to calculate their metric of systemic risk, and then when you want to evaluate the impact of a particular regulation, again, we're looking only at collateralization. There's different dynamics of different regulations. Again, I can model all of those. That's not the problem. Here, I just need to build up what the impact of each of a collateralization means, putting money down. But this is the approach is pretty generic in and of itself. It doesn't depend on using this regulation, okay? And it has on system stability. Okay, so let me just help you in this because some of the terminology gets sticky. So counterparty credit risk, right? This is just a capital requirements regulations. It's just the risk that somebody you've entered into a contract, a derivative, a swap, what have you, defaults, okay? When you put on collateralization, what you're doing is trying to mitigate the cost of that, all right? This just comes right out of the EU definitions. And now, what you want to do then is have, in estimating that counterparty risk at the bank level between two things, there's a standard measure for that, which is called effectivized expected positive exposure. It's estimated like that. I'm not going to. And that it's just the single real number evaluation that quantifies the losses suffered in case of a default of the counterparty, all right? And that this is basically your standard measure of loss, of risk within the system. Okay. Now to give you a sense then how we're going to build this out, we have to have a systemic risk architecture. Again, we have two sets of inputs. We're going to have our financial system generator, okay, that's going to have a distribution sampler for our systems. We're going to generate counterparties, trades, and trade relations. We have regulations, and that goes into our financial system database, data trade. We're going to have regulations 1, 2, and 3. And that's going to all input into give you the input configuration. We're going to use what's called the open source risk engine, and I'll give you some of that in a moment. And that's going to produce a set of outputs, those are sort of risk analytics outputs that we'll then use to give you the risk data, that puts it out, gives you the risk data for each of those financial systems that we then compare under regulation, in the case of regulation 1, with or without. Now we're going to do the data visualization and data mining to show you what the results are. Okay. And now, so just to tell you what ORE, this is out of the FinTech lab in the Data Science Institute. If you haven't visited our website, please do. There's a demo there that allows you to go and look at the open source risk engine. It's open source means you can go into the GitHub there, use the whole demo. You can go there, go into the GitHub, you download 400,000 lines of C++ code and knock yourself out. It's based on QuantLibs, which is a standard, industry standard of all of these back-end codes and formulas. It can compute the EPE, the portfolio, the large Monte Carlo simulations, and all of the other standard techniques. It's just a reference of the implementation of risk, okay, and it really becomes a benchmark when we think of modeling banks and that can be used against the proprietary models that banks have. So again, just you can go to the FinTech lab.
Have you considered packaging your code?
Huh?
Have you considered packaging your code for those of us who don't like compiling C code?
Yeah, you can. There are different versions out there that you can get. I mean, I could talk to you about it if you want. Yeah.
I'm more than happy to. Well, I don't know, give it a shot for packaging, but installing C++ code on Windows is really rough.
It's not too bad to download. I had CEPA students in the capstone do it. So, right, and I've had and I'm even having to say CEPA students do NLP in some of them, you know. So you got to train up, but I think you've got to start on that. So I bet you could, given where it is. The key is though you have to have input data on the trades and so forth. Most of that's based on pseudodata because it's proprietary data. So that's the key on running those simulations. So that's a different conversation. All right, so just so you can see the flow of data and how it works through the ORE, right? You have your input, you'll have your trade, your market data, your configuration, your portfolio loading, your curve. So a lot of this has to all be prefixed in there. These are from standard models on this. And then it'll produce the net present value reports, the cash flow reports. It'll also give you the aggregate collateral modeling exposures and so on, and all of the other cubes that you can then do your visualization off. And there we also have, what we did do is a visualization on top of it. So while you have the aggregate code there, we put a nice overlay of sort of like a very infographic view of understanding risk. So again, please feel free to take a look. Here's the Monte Carlo simulations. Again, this is just 5 interest rate swap scenarios over 10 years. When it calculates out all of the risk metrics, it's going to be using all of these and taking averages over it. There are different ways to do it. You can take tails, you can take averages, you can take medians, but this is what's going to be looking at your averages there. Okay, so now let's go back to the meat. So you're going to have a bank is going to enter into your derivative contract, right, with a particular exposure of CCR. Now, the problem is that these derivatives have very long exposures, sometimes several decades, right? And their notional value could be in hundreds of trillions of dollars. So that's huge, huge risk. And in response to the 2008 crisis, we saw the banks are now required to mitigate the CCR by posting both initial margin and variation margin. Again, initial margin is the first lump of money you put up front. Variation margin is when there's market changes that goes on sometimes daily. Okay, now if I'm going to test the hypothesis that now that there's this expert judgment would say that collateralization should reduce systemic risk, right? One of the reasons why we created derivatives and did securitization was to reduce systemic risk, to spread risk throughout the system. Okay, that was one of the motivations why we introduced, actually the government introduced securitization in the first place. So that's a hypothesis. Can we test that? All right, and so let's see what that might do. So the simulation then, we're going to move from no collateralization all the way down to full collateralization. And there's variations in collateralization system depending on collateralization extent, depending on various contracts. And then we're going to just use, in the first case, a small financial system with 6 counterparties just trading in interest rate swaps, FX forwards. Okay, again, this is generalizable. If you look at the result of what happens then, you can see, just running through all of the simulations you get, you see that the EEPE, right, when you aggregate up, moves from, when you move from no collateralization, blue to green, right, you get a significant reduction in the total risk EEP in the system, right? That is so therefore, the total cost of resolving a system that goes into failure reduces, right? That's the sort of the too big to fail conversation. It also reduces the total EEP of all counterparties individually. So not only does it reduce the cost of resolving the system as a whole, aggregate, like moved all around, each bank, each institution, right, will be less costly to resolve if they too go into failure. Okay. Well, what you see here on the bottom part is that collateralization has virtually no impact on the distribution of risk within the system. So if we thought that that risk was actually reduced by spreading the distribution of risk, right? Not just the amount, but the distribution of risk. Then what we're seeing here is that, in fact, that's not necessary. Collateralization is not the means to do it. Yes?
There's a great paper that actually supports this, but not in such a quantitative way, that was done by the European Banking Authority right after the Greek financial crisis.
Oh, okay.
And you look at exactly that issue, and I think they would really like to see this.
Oh, great.
I'll send you the link.
Oh, excellent. Thank you. Thank you very much. I appreciate that. That's great. There's one other thing that you see, that everybody always works on a small part of it, but bringing it all together is very hard. So, but thank you very much. So now let's think of, is this scalable? How robust is this result? Does it hold when we try and scale? So what we're going to do here is do just a random generation of financial trades, right? This is going to be out of a Poisson distribution, and we know Poisson sequences are really difficult to do. So what we're going to just do is use the Python library here of network X, and we're going to randomly generate. Generation is going to rely on the numpy random. So anybody who's like into the Python libraries, this should tell you exactly how we're just randomly generating this. We just want to make sure that the trades and the relationships are being pulled together in a way that makes sense, that can allow for different types of configurations, and that we're just not going to have, we just only won't have this big sparsity that will just drive the result of, results. Okay. And here again, when you just look at the results, and I'm just giving you a little bit of slice, you can see the histogram of the relative reduction in, again, the EEP of all the netting sets. The netting sets is when you take a group, your group of all of your like trades, right? Because now it's a system, a big system, not just a system. Then you're gonna, you can see that in fact those reduce over time, that predominantly there's a reduction. But you also see very far out in the tail end over there, you actually can have an increase in risk. And that happens when you have very extreme contracts or trades that are out of the money. Okay, that is that they are very either high or low of the market price. Okay. In those cases, collateralization can actually increase risk. And you see that again. You see that again when you look at the increase and decreases on the netting sets when we look at the regimes moving from the collateralization to from no collateralization all the way down. And you see eventually that the more collateralization, that kind of goes away. All right. So you get kind of an interesting result that there are conditions under which collateralization can actually lead to more risk. It's rare, but still it's worth knowing. And it happens, of course, in all the cases, it's case when you don't want it to happen, when you have extreme netting sets that are out of the money, right? That are either going to be big losses. But you also know that even though the relative exposure may be in large and the absolute exposure when you look at the aggregate is sort of really small. So for the system as a whole, it may not be. Yes?
Are you going to give a specific example of a type of trade that generates that result?
I have it in the case, but I didn't have it.
I was just curious.
So an out of the money thing would be a case where you have.
Is it degree of out of the moneyness?
No, so when you're deep, or so like deep in the money, I guess is an option with the excise price. Here, I'll give you the definition, so there's no bringing down. Okay, it's a type of option is considered intrinsic value, right? So it has to be calculated in a way, and that the striking price from the underlying asset. So, right, that's the difference there. And you look if you're either really below that or really high above that. That when you have big differences from that actual price, that's when you can get these kind of perverse outcomes. That's the example. Right? So if it's significantly below or above, right? The put option, the market price of the underlying asset. That's when you will get this type of perverse outcome.
Are there typically cases where there's been leverage or not necessarily?
Not necessarily. It just could be there's swings, market moves. It could be some, bad scandal. It could be Enron. There was puts out there. Enron collapses. You've got it, right? And you're in counterparties, or it could be Lehman.
So these are just terribly out of the money trades as opposed to something, a certain type of.
So, but that's exactly when you want collateralization to work, right? When you're in those rare extreme events. That's why you actually impose collateralization on them. So that's the interesting part. Again, it's still relatively small. It's only going to affect these very tail end again. But again, it doesn't mean that they don't happen. And if you look at, if you were to do this over and over and over again, you may find those tail end events, even though it's small, they happen at exactly the worst times. And they can have those different types of systemic ripples. That, I haven't done any of that. I haven't tested that. It's a conjecture. It may or may not be true, but that is one of the things that you could test now that you know this pattern. And this is just right from the data mining. This is not being generated from anything else but straight out, did you increase or decrease under what, given this distribution of random generated trades, okay? From that persona distribution. That's it, that's all it came from, okay? And it was repeated, it was repeated, let me see, how many times was it repeated? Generate 10 financial systems with 30 to 50 counterparties, right? Resulting in 2,360 trades in total. So it's a lot. They're relatively big. For big data, that's small, but it can get. You can see that you can actually generalize this significantly and still maintain the robustness of the results. Okay. All right. So So what's the next step? So again, we're going to work on some of the more of the statistical robustness metrics here, doing some more diagnostics, understanding those tail end results. There are other different types of regulations actually to look at as well. Capitalization, and then the central clearing, which I think are important. And the other notion that is beginning to bubble in the discussion is the notion of credit risk versus liquidity risk. And most of the regulations have focused on credit risk. After the financial crisis, really regulations and regulators saw the crisis and the way to mediate and mitigate the risks associated with the large banks is by forcing them to hold more capital absorbing, risk absorbing capital, all right? But by doing that, then what they've done is they have a lot of capital stuck in the banks that cannot be used out in the system. So what you have in essence is a trade-off between managing credit risk versus creating liquidity risk, all right? And that may be the next bubble that takes place. There's always going to be you never get rid of risk, I think is the way we're seeing. It never goes away. It's how you manage it, how you observe it, and how you can be sort of very proactive in sort of when you're in those tail end events, being able to jump in and address them immediately before it becomes a crisis. And therefore understanding where the next bubble takes place or how one would then, if it becomes a liquidity crisis, how one then can mitigate, what are the appropriate regulatory measures or appropriate steps to take, I think is really important. And this is the type of analysis that enables you to do that. So, yes?
Just to be clear, on the last example, you're exclusively looking at OTC derivative transactions?
Yeah, that was yeah, because, yes, those are OTC derivative transactions, yes. So, yes, are there any questions? Yes?
I was thinking about sort of the real world implications of this. One thing that I struggle with is how to properly measure and account for linked risks within their system. So I'm sort of fascinated by your tail events where collateralization increases risk and just start trying to think through how does that happen. And I'm wondering if you're able to account for cases where correlated risks within the system are either leveraging or implicitly hedging out risk. You know what I mean? So if a bank held one security that happened to, without intending it, they held a second security with a correlated risk.
Yep.
They're essentially leveraging that risk, or maybe it has the opposite risk and they have a natural hedge in place. Or similarly thinking about, I come from a commodities background, and one thing the banks always struggle with is justifying to risk managers right-way risk.
That's right.
So an implicit hedge that already exists. Just thinking about your tail events, I'm wondering if there's some sort of unwitting leverage in the system.
So,
and can you capture that?
It'd be interesting to get the data that now that you have the simulation, you now know what to be looking for on the data, correct? To actually be able to test that hypothesis. One thing now, because of the new regs, is that the banks can't re-hypothesize the initial margin. The collateralization. And therefore what you see within the banks is a sort of a collective action, a common pools fight over the existing cash, money, collateral that can be used for hedging. So these become very intense conversations. So it would be interesting to see how, if you can get that kind of data. And we have another paper on daisy chains, which is the hedging of the hedgings of the hedgings. And what it shows is that there is an optimal length of your daisy chain. Daisy chain being, how banks, when they go into a hedge, a derivative, they then hedge to the hedge, and then they hedge, and they wind up almost creating a complete daisy chain. And that's lovely. However, it's very expensive because it's really not an optimal use of your capital. And that really there is an optimal daisy chain. It's actually you can figure it out. It's a lattice structure. But it's really, when you do the optimal daisy chains on that, you can get almost something like an 83% reduction in the amount of collateral you have to put up, which is huge. So that, as a paper published, so I'm happy to share that as well. Yes?
Quick question, have you had time yet to look at the tier, to bring in different tiers, looking at that capital quality, and do you think it would be relevant?
Capital quality. I'm sure there is a difference in capital quality. I'm not.
Was it using the already available tier 1, tier 2, tier 3 as a shortcut to being, because it's so much work. So in terms of that.
I have not. We have not. But it's an interesting. So the key is getting to actually run these now. Now so a lot of this is being based and simulated off of real data, client data, which I don't know what client it is. I don't know, right? But they're predominantly large European financial institutions and a few American. But that's where a lot of the trade data gets simulated off of. But I don't think I have the tier.
That might be very useful.
It might be, yes. So thank you. Thank you. Any other questions?
What I'm hearing from this talk is that there's probably a lot of benefit for better data sharing from the private corporations.
Yes.
So what are the what are the current challenges?
Yes. So that's a whole one of the reasons why the FinTech Lab exists is in fact to get the ORE actually provides a benchmark, if you will, for both the proprietary models and the banks and regulators to have a common conversation, because you can open it up and see what all the assumptions are, and then be able to have I would say an intelligent conversation as to why you differ in your estimates, as why you should have this amount of capital reserves versus this amount. In addition, working with ArcadiaSoft, which is a consortium of all the large banks, we're trying to be able to get the data, so at least the slices of the data, to be able to put into these types of models to run those estimates. And that, as you know, ArcadiaSoft itself is having limited success in getting off, but it's beginning to develop. But we hope, if all goes well, we would be the repository of those slices, and that would be fabulous. Yes. We're also working with the OFR to try and on some of their efforts to do data governance issues and so on.
So are there any other questions? If not, let's thank Sharyn again for today's talk.
Thank you.